We'll continue our discussion on optical amplifiers. So the last class we looked at how a pre-amplifier at the receiver can improve our sensitivity by roughly an order of magnitude, right? So today let's look at inline amplifiers. So for a long haul link, right, because of the fiber attenuation, once you go beyond, let's say 100 kilometers, you need amplifiers along the fiber link to boost up the signal to compensate for the loss in the fiber, right? So let's look at what effect this has on the performance of the link. Okay, so again, the idea is, so you have a long link, so every after every distance LA, we put an optical amplifier, right, to boost up the signal. So each of these sections are LA in length. So you have an amplifier of gain G, and then typically we have an optical filter after each amplifier, as we discussed last time, to limit the noise added by the amplifier. Okay, and so basically you have some n number of these over the entire link length. Right, so the entire link length here is L. Okay, and so if NA is the number of amplifiers, that's just L over LA. Right, let's assume that there's an amplifier just before the receiver also. Okay, so how does the, if you look at the optical power, right, as a function of distance along the link, so we start from some power here, which is the transmitted power, right? And then due to fiber attenuation, right, the power is falling. So let's say I'm plotting power, optical power in dBm or so. Right, so then because of the fiber, this power will fall down, right? And in dBm, it will be a linear loss with length, right? So the attenuation coefficient in dB per kilometer times the length. Okay? And so this reduction here will be just the attenuation coefficient of the fiber in dB per kilometer times LA, right? That's how much the power will fall here. Okay, and then to compensate for this, we put an amplifier with gain G, which boosts the power back up to the transmitted level. So that means, of course, that so G is equal to so G in dB is equal to alpha dB times L, or in natural units, G is just e to the alpha times L, right? So we compensate for the loss with the amplifier here, right? So the power is brought back up to the transmitted level, and then again in the next section it goes down, right? And the same amount of loss, so it goes back down to the same level. Okay, and yeah, so on for each section. and then as the receiver finally basically we boost it back again up to the transmitted level. So the received power is equal to the transmitted power. Okay, so if that was the only thing that happening, then that's great, right? Basically, we compensate for the entire loss along the link, and we basically made our receive power equal to the transmitted power. So we can indefinitely increase the link length, right? If we can just put on amplifiers, then we would just indefinitely increase the link. But of course, that's not possible, right? And that's because, as we discussed, every amplifier not only amplifies the signal, but it's actually adding its own noise. Right, so the optical SNR will actually keep degrading. So we discussed the concept of noise figure, right? So the output SNR is lower than the input SNR. So after each amplifier, my optical SNR will go down. So to understand that, so let's assume that from the transmitter there is very little noise, very little optical noise, right? So basically, the SNR coming out of the transmitter is very high. Then, so you reach the first amplifier here, right? And so you can even assume some level. So let's say, so we saw typically, like for example, the noise level, the optical SNR coming out of semiconductor lasers could be as high as like 60 dB or higher, right? So this, if I plot a noise optical power here, this is like, you can imagine something like 60 dB or lower than this level. Okay, so if this is 0 dBm, this is like minus 60 dBm, the noise level. Okay, and so the noise level is some very low number. For all practical purposes, negligible until we reach the first amplifier, right? And so we discussed last time that the optical amplifier adds spontaneous emission noise, right? So here, basically, we'll add a noise which is equal to the spontaneous emission noise. Okay. So this level is given by this. So last time, recall, we had this spontaneous emission noise power, which was something like the noise spectral density for spontaneous emission times the filter bandwidth, right? So you're basically adding that amount of noise here. Okay, and okay, so then after that, the next section, just like the signal, this noise power will also get attenuated, right? So it's an optical power, so it will also experience the fiber propagation loss. So the noise power will also get attenuated by the same amount, right? This alpha times L. Okay, so the noise level when I reach the next amplifier, this is down by a factor G, right? So this level here is PSP divided by G. Okay, so now what happens? Next amplifier, I have some input noise level here. Okay, so that erase this. Okay, so this, now I have a gain G, so the noise power is boosted up back to this level here. And not only that, now this amplifier will add its own PSP, right? It will add its own spontaneous emission noise. So you'll have a PSP plus you'll have PSP from this amplifier. The total will be 2 PSP, right? Or in dB units, this will be 3 dB higher. Okay, so you can see that basically after every amplifier, my signal is restored to the same level as the transmitter, but my noise actually goes up by a factor of 2 or 3 dB. Okay, similarly in the next section, so this will go down by a factor of g, so this will reach now 3 dB higher than this level, right? And then again you have again, now you go back up to this 2 PSP. Now you add another spontaneous emission noise from the next amplifier, and this will go up again 3 dB. Sorry, not 3 dB now because this will be 2. So 2 plus 1, so this will go to 3 times PSP. So this won't be 3 dB. So in linear units, you're adding the same power, but in dB, you won't be adding the same in dB units, right? Anyway, but you can see that after every amplifier, the noise level will increase by an amount given by the spontaneous emission noise. So equivalently, if I see the optical SNR, right? So you see that this noise power is going up. The signal level is sort of remaining constant, which means the optical signal to noise ratio, right, which is sort of the ratio of the signal power divided by the noise power, that will keep going down after every, right, so it will go down here by some amount because of this added noise. Then it will go down again at the next amplifier, it will go down again, right? So this will be the optical SNR, which keeps going down. So if I start with some optical SNR which is at, let's say, 60 dB or something here, because of these amplifiers, it will keep going down, and at the receiver now my optical SNR is much lower. Okay, so basically in summary, if we plot with the distance along the link, so different optical power. So if you look at the signal power, that's constant, neglecting this loss and gain in the middle, right? So if I just look at the power after each amplifier, that's remaining constant. Okay. If I look at the spontaneous emission noise, the accumulated spontaneous emission noise, right, that's going up like this, because each time I'm adding something here. So the ratio of these two, which is the optical SNR, is going down. Right? And finally, you know that basically the optical SNR here at the receiver will determine my electrical SNR and hence the bit error rate. Okay, so you can see that basically from this argument, although we restore the signal back to the original level, our SNR will actually keep going down. And so let's say I want to operate at a particular bit error rate, I require a particular SNR, right? And so that will determine a maximum. So this is the SNR minimum I can have for that particular bit rate. So that will determine the maximum link length I can have. Okay, so I can't indefinitely increase my link length just by adding amplifiers. Okay, so this spontaneous emission noise which is added is also sometimes known as amplified spontaneous emission noise, or ASE. Okay, so recall that this noise spectral density, right? This was this spontaneous emission factor times the photon energy times this gain. Okay, so it's something like you have some spontaneously emitted photons within the amplifier which acquire the gain due to the amplifier. So that's why it's known as amplified spontaneous emission noise. Okay, so what is the total this AC noise which is accumulated? Right? So I mean each amplifier is just adding this amount of noise, we know, right? So basically the total noise accumulated, so total right, so this is the total spontaneous emission noise which is accumulated in the link. So I can just write that as a number of amplifiers times the noise added by each amplifier, right? And then there is a factor of 2 here to include 2 polarizations, right? So we have 2 sort of independent orthogonal polarizations which can propagate in the fiber, right? Horizontal or vertical, for example. And so each component has its own noise because the spontaneously emitted photons can have random polarization. So both these independent polarizations have their own noise. So the total noise, if you include both polarizations, is 2 times. Okay. Okay, so or if we include this expression for the noise spectral density of the spontaneous emission, okay, so the total accumulated noise goes as scales with the number of amplifiers in the link and the gain of each amplifier, right? Or the product of these two is like the total gain of the amplifier, or the total gain in the link. Okay, and then what is this optical SNR here? So that's what is the signal level here? That's just the transmitted power. And then the what is the noise power? The total accumulated noise power at the end is just this, right? So this is the optical SNR at the receiver. Right? Okay, so that's my optical SNR at the receiver. Okay, so you can see that again, as I'm increasing the number of amplifiers or the link length, my optical SNR is going down, right, for a given transmitted power. But of course, finally, so we detect the optical power onto the photodetector, and then we have this receiver circuit to make a decision, right? So finally, the electrical SNR will determine the bit error rate, right? So the electrical SNR, you know, is like the square of the average photocurrent from the photodetector divided by the variance in the photocurrent, which is also the noise variance of the noise product. Okay, so here in the numerator, I have just responsivity times the signal power. The received power is equal to the transmitted power. And then what will be this variance in the electrical current here? Recall that is dominated by what is known as we saw last time, the beating between the signal and the spontaneous emission noise. right? So we said our current photocurrent has three terms. One is just this mean value. Then we have two more terms which act as noise, right? One is the beating between the main signal and the spontaneous emission noise, and the other one was just the spontaneous emission noise beating with itself. And we typically said that this would be much bigger than this. Okay. So here basically we just include in the noise the beating between the signal and the spontaneous emission noise. But it won't be. So in the last class we had an expression for this just for a single amplifier, right? Now we have n of these. So the total noise will be the number of amplifiers times this noise for a single amplifier. Okay, and recall this expression we had derived last time, the beating. So that goes as something like this: co-responsivity squared and the gain of the amplifier times the input power to the amplifier, and then this spontaneous emission noise power spectral density times the bandwidth of the electrical bandwidth of the receiver. Okay, so this expression we had derived in the last class. Okay, so now what is P in for each amplifier here? Right, so what is P in is basically the power entering the amplifier here. And you can see that that is just 1 over G times the transmitted power. Right, so the P in here for each amplifier is just the transmitted power divided by the amplifier gain. Or in other words, this G times P in is just the transmitted power. Okay, so I can write this as that. Okay, and then so now we can plug this expression here to get the electrical SNR. Okay, so we end up responsibilities cancel out, one factor of the power cancels out. Okay, so basically we want to relate this electrical SNR to the optical SNR that we found here. So the optical SNR has this bandwidth of the optical filter that we are using. So basically we divide and multiply by this delta nu optical here. Yeah, so basically we end up right, this multiplied divided by delta nu optical, and this thing is just the optical SNR. Okay, so the electrical SNR is related to the optical SNR which is received by this factor of the ratio of the bandwidth of the optical filter to the bandwidth of the electrical bandwidth of the optical receiver. Okay, and typically we saw last time this ratio is typically much bigger than 1. Right, so delta F, like a few gigahertz, delta nu optical is typically hundreds of gigahertz or few terahertz. But you can see that if you want a lower electrical SNR for the same optical SNR, you want a narrower optical filter. Okay, we can also substitute the expression for this noise spectral density for the spontaneous emission to get the expression in terms of okay, so for a given link length and a given spacing between each amplifier, right? So this NA is basically L over LA, right? And the gain you saw is e to the alpha LA, right? Which is the e to the minus alpha LA is the loss in this section, right? So from here, so if I write LA as then 1 over alpha log of G, then you can see the number of amplifiers scales with the gain of each amplifier and the total link length like that. So if you put this expression for NA into here, basically you see that the electrical SNR is proportional to, so if I put for NA this alpha L divided by log of G, so I get log of G in the numerator now, right? So the scaling with the gain of each amplifier is like this, and the scaling with length is 1 over L, right? So I just put this here, so I get L in the denominator and log G in the numerator. Okay, so basically the electrical SNR that I obtain, right, you can see that it's going down with increasing total link length, even though I use amplifiers to restore the signal, right? And it's scaling with the gain of each amplifier like that. So log of G increases slower than just linear G, right? So this actually, this thing goes down with increasing G, right? So actually the electrical SNR also falls with increasing G, the gain of each amplifier. So what does that mean? So what is G, right? G is basically the amount of gain that I required to compensate the loss in this section. So if I, for a given link length L, if I have fewer amplifiers, then this G needs to be larger, right? Or if I have more amplifiers for the same link length, then the gain of each amplifier G is lower, right? So here you can see if I use fewer amplifiers, with each amplifier having a larger gain, then actually my electrical SNR will be lower. Okay, so although I'm restoring the power after each amplifier, it matters how many amplifiers I'm using, right? So from here you can see that it's better if I use more amplifiers. with each amplifier having a smaller gain. Right? To get a higher SNR receiver and lower bit error. Right, and we've discussed this already. So basically, the bit error rate depends on this Q factor, right? And the Q factor is something like the square root of the SNR, right? So if the SNR goes down, then the bit error rate goes up. Right? So you can see that you can improve the performance by having more amplifiers. So let's say you put 5 amplifiers. Compared to that, if you had 10 amplifiers, that would be better, with each amplifier having half the gain compared to when you have 5 amplifiers. Or if you go to 20 amplifiers, that's even better. Right? As you keep increasing the number of amplifiers for a given link length, you improve the electrical efficiency or reduce the bit error rate for a given transmitted power. Okay, so of course there's a limit, right? Like you can't put hundreds of amplifiers because it costs money, right? So basically you settle for, from this expression you can find out so what this G would be is, so let's say I want to operate the link at some particular bit error rate, right? Typically again you set it to some level like 10 to the minus 9, and then for that 10 to the minus 9 level, for a given link length L, I can calculate what this G would be, right? So the 10 to the minus 9 BER again would correspond to some Q of 6. From there I calculate, okay, that corresponds to an SNR of something like Q squared, which is 36, and from there I can calculate given transmitted power, etc., what this G should be. So how many number of amplifiers I need, right? And then basically that many amplifiers are enough. I can go to higher number of amplifiers. The bit error rate will reduce even further, but I don't really care. Once it's 10 to the minus 9, I can sort of compensate for the errors and operate manually. So if it goes further down, then I don't worry about it. So that's the minimum number of amplifiers I use. Okay, so if you do that, for example, so you can get a curve something like the total, so the maximum possible link length as a function of the amplifier spacing here. Okay, so this both are in kilometers. Right, so you can see from here. So for a given bit error rate, I need a particular SNR. Right, so for a particular SNR, you can see that the link length sort of inversely scales with the gain. Again, so this factor goes down with increasing gain. So basically, this L, I can get a larger L with a smaller G, and a smaller G would mean a smaller LA, right? Because again, G is just e to the alpha. Okay, so if I have smaller amplifier spacing, which means I need more amplifiers, then my link length would, the link length that I can obtain, total link length would be higher. And as I increase the spacing between the amplifiers, this link length will go down. Okay? So you get obtain curves like this. Okay, so this is again, you set your performance to some level. So let's say we are 10 to the minus 9, Q of 6. Actually, these curves are for slightly larger values of something like Q equal to 10, and this is like 10 to the minus 12. So electrical SNR is something like 100 Q square or 20 dB. Okay, and then you have other parameters here like so loss coefficient. So again, let's say you're working at 50.2 dB per kilometer. Okay, and then bandwidth. So the electrical bandwidth 10 gigahertz, which is typically roughly half the bit rate, right? And so the spontaneous emission factor typically taking around 1.6, which gives you a noise figure for each amplifier of about 5 dB. Okay, so these are some typical numbers. Right, so for a given VER that you want to operate, you get curves like this. And each curve is down for a different transmitted power. Right, so this is 0.2 milliwatt. This is 0.5 milliwatt. This is 1 milliwatt. 2 milliwatt, right? As I'm increasing my transmitted power, of course, I can go to a longer distance because the SNR is proportional to the transmitted power. And for a given transmitted power, as I increase the amplifier spacing, the total link length goes down. So let me put some numbers here. Okay, so the amplifier spacings we are talking about are typically tens of kilometers, you can see 200 kilometers. And the total link lengths we can obtain are really long transcontinental type of lengths here. Okay, so this is into 10 to the 3 kilometers, so 1000 kilometers. So this is 5000 kilometers, 10,000. Okay, so we can really go up to like, you can see like transcontinental lengths using like milliwatt powers and an amplifier every like. So typical amplifier spacings are like 80 kilometers for these long haul intercontinental links. So yeah, we just discussed this. There's a question: having lesser number of amplifiers with larger gain is equivalent to having larger number of amplifiers with smaller gain, right? So we just discussed that it is not, right? What you want here is more amplifiers, each with a smaller gain, right? You want a lower amplifier spacing for if you want to go longer distances. So, okay. Yeah, I hope that this discussion answered your question. So, this dependence here of the curve is right. So, you can see from here for a given SNR, so L is proportional to so L is proportional to log of G. So log of G is alpha times LA divided by G minus 1. Again, now G typically for each amplifier will be at least 10 or more. So G minus 1 roughly will be G, right? So that is e to the. So this is the function dependence here. Right, so you can see as alpha is increasing, as LA is increasing, the denominator is increasing much more than the numerator, so L goes up. Okay, any questions? Okay, so then we'll sort of discuss the performance of optical amplifiers, treating them like a black box so far, right? As a component in our communication links. Let's now just briefly look at sort of the specific types of optical amplifiers that are used, and how some of the parameters like the saturation power, gain, that get etc. depends on the particular characteristics of the type of amplifier that we use. So there are three main types of optical amplifiers which are used in communication links. One is the semiconductor optical amplifier, which is basically the semiconductor laser, the same device, but except that the ends are not high reflecting, so you don't form a cavity. The second one is the EDFA or erbium doped fiber amplifier, which is basically a length of fiber with erbium atoms doped into the core, right? And then we send a pump laser which causes population inversion for these erbium atoms, and that can provide gain at telecom wavelengths. Nice thing about EDFAs is that, like, since they are a fiber device, you can sort of integrate them into fiber links. And then the third type is a Raman amplifier. It basically works on this nonlinear effect of Raman scattering that we had discussed towards the beginning of the course, and that is also fiber based. So we have three types, right? SOA, EDFA, and Raman. So just briefly discussed each of these without going into too many details. So starting with the SOA or semiconductor optical amplifier, right? It's basically the same device that we have discussed for the semiconductor laser, right? So you have a PN junction with an active region in between, and typically you have a double heterojunction. You forward bias the PN junction, you send a current, right? And if you make the active region small enough and send a current large enough, you can achieve population inversion in the active region or effective gain. But now instead of these facets being sealed and polished for high reflectivity, they are actually coated with anti-reflection coatings. Okay, because basically what we want is a traveling wave amplifier. So we want input optical power coming in from one end, then acquiring gain as it propagates here, and then come out from the other end. So we don't want reflections. Right, so we want a traveling wave amplifier, so we have anti-reflection coatings on both ends. Okay, so depending on the current here, you get some gain, right? So this gain is dependent on the function of the current. So typical gain values that one can get. So here I'm plotting wavelength. Around 1.5 micron. So typically you get some curve like this. Okay, so there is a gain over a range of wavelengths. So you have some gain bandwidth, but the gain curve is not smooth. Typically it has some ripples like this. Okay, and these ripples are basically coming from these reflections. So ideally you want 0% reflectivity at each end, right? Whatever comes in goes in, and whatever comes out incident from the other end here comes out. But even a few percent or very small reflectivity at each end actually causes the light to sort of bounce back and forth here and create like a Fabry-Perot cavity, right? And basically, depending on the length, here you get these fringes. Okay. And you can imagine, so now if the reflectivity of the facet is higher, then these ripples will be actually more pronounced. Okay. So to obtain a smooth gain curve here, you want to suppress the reflection here as low as possible. So one figure of merit that is used is so that this ripple let's say if you want the ripple amplitude of this ripple to be sort of less than 3 dB, right? So you can see the absolute gain values we can get here. Maximum gain value is around 20 dB or 100 times. So if you want to limit the fringes here to less than 3 dB, then that puts a condition on the reflectivity of the facets here. So basically, the gain that you get from the amplifier times the reflectivity at each facet here, that should be less than about 0.17. Okay, to limit the ripples to below. Okay, so you can see that. So for example, if you have a gain of 20 dB here, which means V is 100, that means that the reflectivity has to be less than 1.7 times 10 to the minus 3, right? Or 0.17%. Right? So you can see that you really need very good AR coatings here. Okay? Otherwise, the ripples in the gain will be very large. So, for example, if you want to amplify multiple wavelengths here, then some will have a very large gain, some will have a very low gain. So, you want a smooth gain curve. Okay, so this gain that we're talking, this capital G, right? We saw it, so we can write it as something like exponential of small g times the length of the amplifier. But this small g is the gain coefficient. So this gain coefficient small g, we sort of seen this already when we were studying lasers, right? It depends on the carrier concentration. So it depends on how many carriers you pump into the active region here. Sigma g, the cross section. Right, so we've seen this expression already. So this is the volume of the active region. This is the number of carriers or electron hole pairs pumped into the active region. This is the number required for transparency or gain of 0. Just the onset of population inversion, basically. Right. So this is the confinement factor of the mode. Right. Again, so you have some optical mode like this here traveling. Confinement factor. And this is the cross section. Right. So this is the differential gain. Okay. So same thing here because the device is the same. And we also saw this that, so if you look at the dynamics of how the carriers are varying with time, right? So there is an injected current which is increasing the number of carriers. Then there is a recombination rate of the carriers, right? So there is some carrier lifetime, right, before which the carriers recombine here in the active region. So that decreases the number of carriers. And then you have stimulated emission, right? So that of course depends on this gain factor. Okay. So recall when we were discussing lasers, we had a term like G times the number of photons here, right? So we just written that term slightly differently. It's the same term G, capital G times number of photons. You just written in terms of the optical power, right? And sort of written out the G in terms of the cross section and the number of carriers. A effective is this is the mode area of the this mode traveling here, right? So P over A is something like the intensity in the active region. Okay, so now again, let's say I have a steady current, DC current here. Then in steady state, my number of carriers reach an equilibrium, right? So dN by dt is 0. So if you do that, you can see that you will get the effective gain coefficient, right? So you can solve for n, right? And you can put n into this expression to get small g. So you can see that small g scales with optical power like this. Okay, so directly from the this dynamic equation for the carriers that we have coupled to the photons through simulated emission, we get this saturation behavior of the gain. And so from here you can check that, so G naught comes out to be, of course, proportional to the current. Right? So what peak gain I can get, of course, scales with the current. The more current I send in, the more carriers I pump in, and the more gain I get. And this saturation power P sat comes out to be okay. So the saturation power depends on the effective mode area and inversely proportional to this cross section, and the carrier lifetime. Okay. So again, recall that saturation power is sort of a measure of how much maximum power you can get out of the amplifier, right? So if you want a higher saturation power, you can see that you need a larger effective area, the larger mode here, and you need a small carrier lifetime. So you want the carriers to be combined fast. Right? So if you put the typical values for like in-gas feed devices, for example, typically this comes out to be around 10 millivolts. Okay. So those are the typical saturation values for a semiconductor optical amplifier at telecom. Okay, so you can see that if you use an SOA, the maximum power typically that you can get out is the order of 10 millivolts. Okay, so you can't. That's the level power coming out. If you want more power, like 100 milliwatts or larger, then you can't use SOAs. And then the other important metric for amplifiers, of course, is noise figure. So for the SOA, the noise figure also depends on sort of this G. Right. So again, recall noise. This figure is basically determined by sort of how strong the spontaneous emission is compared to the stimulated emission. So you want to be deep into the stimulated emission regime where you have large gain, right, for a low noise. So this noise figure typically can be written like this. Okay, so it depends on the number of carriers here in the active region. So this is something like the population inversion, right? So this gives you the level of the population inversion, something like N2 by N2 minus N1. And then there is this factor of how much above the internal loss you are. So how much is the gain factor above the internal loss? Okay, so you can see that once you go deep into the stimulated emission regime, so for N much bigger than the transparency number and for gain much bigger than the internal loss, right? So recall that. So your G, yeah, so G depends on the current here. So and N also depends on the current. So basically, you want to send in large enough current such that you're in this regime, and then the noise figure will approach 2, right, for these values. Typically, if you take commercial SOAs under sort of standard operating conditions, typically, so 2 means 3 dB, right? But typically, that's the best one can do. Typically, SOAs have between like 5 to 7 dB noise figure. It's typical. Minimum. Okay, and there are some more details, of course, that we are not going into. So for communication applications, of course, we are looking at amplifying pulses, right? Not like a CW kind of analysis. So then, if you take time varying pulses here, then you have to take like these carrier dynamics, and things become more complicated. But the general arguments we've given are true. But it also lets the device also has some bandwidth, right? So you cannot amplify pulses below a certain pulse width. Right? Once the pulses become very narrow, then their bandwidth exceeds the response time of my medium here, and you cannot amplify them. But typically up to sort of like 10 gigabit per second. So if you have 100 picosecond pulses here, typically you can use SOAs. Below that, once you go to tens of picosecond or something, then the SOAs don't respond as well. Okay, so that's the SOA. Any questions? Okay, so let's now discuss the EDFA briefly. Of course, the geography students know from the fiber optics course last semester, we had discussed EDFAs in some detail there. So here we just sort of briefly just revise some of the important aspects and not go into too much detail again. Okay, so this stands for erbium doped fiber amplifier. Okay, so typically what you have is like you have some length of fiber, typically few meters to few tens of meters of fiber, and basically if you look at the core, it is doped with erbium atoms. Okay. So basically, so you have glass here, right? And then erbium forms this complex with a positive charge 3 inside the glass matrix. Okay, the typical doping level here is about 1000 parts per million. Okay, and now if you look at the energy levels of the erbium, so there are sort of 3 main levels here which are useful in amplification of telecom signals. So this ground level here is known as, don't worry about the naming scheme here. Okay, so these are some energy levels for this erbium ion. Okay, and so basically under thermal equilibrium or steady state, your atoms are sitting here in the ground level. You can pump them up to this top level using a 980 nanometer laser. Okay, so this transition corresponds to about 980 nanometer. And then from here to here, there's a fast non-radiative decay. Okay, so this middle level is a metastable state, which means the atoms will pump here quickly, they come here, but then they stay here for some time. Okay, so this forms what is known as a 3-level laser system, right? For people who have lasers. So basically, with enough pump power, you can achieve sort of more atoms here than here, and so you have stimulated emission and lasing, or sorry, stimulated emission gain for this transition here, which is in the C band typically. So this. Okay, typically C band wave, this corresponds to the C band wavelengths, 30 to 1560 nanometers. You can also operate it for slightly lower L band wavelength. So this is C band. You also get EDFAs which work like for slightly higher wavelengths in L band to 1600 nanometer. So the same levels are involved here, just the sort of the vibration sublevels within them are different for these. Anyway, so yeah, so basically in this range between 1.52 or 1.53 typically, 1.53 to 1.6 micron, in that range you can use the EDFA. So the SOA, depending on the material, right? So we saw that depending on the in-gas free material that we use, the mole fractions, we can tune the wavelength of operation. And once you choose a material, typically the gain bandwidth that you get is typically we saw that like tens of nanometer, 20, 30 nanometer or something, right? But so you can make SOAs all the way from like across all the bands because it just depends on the material composition, right? Whereas EDFA, because the material is fixed here, you can only use them for these. But turns out that the minimum loss wavelength for fibers is 1.55, right? So that's the most used wavelength anyway. So that's why EDFAs actually took up really quickly once they were discovered, and that's what enabled sort of this explosion in global connectivity. Just we could go to much nowadays. Okay, so one can also sort of, instead of going through like this, one can also just pump to the top of this metastable state directly. Okay, with you can see this is lower energy, so higher wavelength. So this is 1480 nanometer. So you also have EDFAs with 1480 nanometer pump. Okay, but typically it turns out actually the 980 nanometer pump is more efficient. Okay, so mostly EDFAs have 980 nanometer pump, but sometimes you also see 1480 for other like noise sensitivity. But typically, if you want to use EDFAs with high gain, etc., use 980 nanometer. Okay, so now because sort of you can see that the level of population inversion you're getting is now depends on the pump power, right? The higher pump power you have, the faster you take atoms out here and get here. So if you look at the saturation power for the amplifier, for the EDFA that just scales with the pump power. Okay, so we saw for the SOA it was a constant depending on material parameters, and it was about 10 milliwatts. But for EDFA, it actually depends on the pump power. So I can get more power out of my amplifier if I have more pump power. Okay, so that's an advantage. Yeah, so this length, I forgot to mention here, typically a few meters, let's say between 5 to 20 meters or something. Okay, so typical pump power values range anywhere from, let's say, 10 milliwatt all the way up to even watts. Okay, so there are some super high power amplifiers you see that even have like 10 watt. Okay, so you can span a really big range here. So the output powers can also sort of span similar ranges. So for the SOA, we could only get 10 milliwatts, but with EDFA, we can get much higher powers. Okay, and not only that, like so, if you look at the gain curve in this, so it looks pretty flat within the C band. Okay, so if you have a DWDM signal, you can simultaneously amplify all the wavelengths without much distortion. Okay, and so this saturation power helps because so this is like the total power you can get out. Okay, so let's say if you have now many wavelength channels, you have to add up the power for each channel to get the total power. Okay, so let's say if you have, for example, 10 milliwatt, then maybe you can have 10 channels with 1 milliwatt each. right? But now let's say if you have 1 watt, then you could have like 100 channels with 10 milliwatts, right? And so typical gain values that you can get with the EDFA again also depends on the pump power. Okay, but again you can get anywhere from sort of 10 dB to 30 dB typically. Okay, and so the gain. So we'll discuss this again in more detail in the fiber optics course, but basically if you look at the gain versus pump power for a given length of fiber, typically that scales like this. So initially the gain sort of increases exponentially with pump power, but then it starts saturating, right? Basically this, again, effect of gain saturation. If you look at the gain versus the length of the amplifier, again, it's sort of the gain increases with length up to a certain point, but then actually if you start going even beyond, then the gain actually starts dropping. Okay, and what is happening here is that, so just like you know that the optical fiber has some propagation loss, right? So your pump and signal are propagating within this fiber and they're getting attenuated, right? So pump is obviously getting absorbed also, right? So basically the pump gets fully absorbed within this length of the fiber, and now you have no more pump remaining, right? And then now the signal just doesn't experience stimulated emission. So in the sort of latter end of the fiber, it doesn't see any gain, but actually experiences loss due to just the fiber propagation loss. Okay. So then beyond a certain length, you can actually start having the gain decrease. So you don't want too long a length. There is some optimum length typically for maximum gain. Again, it depends on various parameters that we have discussed. We won't go into the details here. And then finally, the other important metric is noise figure. Okay, so again, if you look at noise figure as a function of amplifier length here, then typically it first increases and then sort of saturates. Okay. So once you get into this gain saturation regime here, now beyond this sort of noise figure starts saturating also. Okay. And so these are for different pump powers. So increasing pump power. Oh, sorry, the other way around. So this is, let's say 2, 5, and 10 milliwatts. So as you increase pump power, noise figure actually gets better. Because as you're increasing pump power, you're increasing stimulated emissions, right? You're increasing the population inversion, and stimulated emission is more dominant over spontaneous emission. So the noise figure is better. Okay, and so typically again you can, with EDFAs you can get noise figure around like 4 dB. So typically 1 or 2 dB lower than maybe SOAs. Okay, so that's it's all about EDFAs. Finally, let's discuss briefly about Raman amplifiers. So Raman scattering we had discussed sort of towards the beginning of the course as a nonlinear response of the fiber channel, and there we were discussing it as a problem which limits the performance of especially WDM links, right? The same effect here can be utilized to get an optical amplifier, right? So basically we use stimulated Raman scattering. So recall so frequency is going this way, wavelength is going this way. So if you have a pump, frequency nu p, right, or wavelength lambda p, then there is this Raman gain response for the silica material, right, which extends all the way up to something like 15 terahertz, right? And so if you have a Stokes or signal wavelength within this gain curve, then it will get amplified. So this is the and recall we could approximate this by like a simple triangle function. So typically, for example, if you use a pump at let's say 1450 nanometer, right, this shift to the peak of the gain is about 90 nanometer, right? So the signal wavelength will get is about 50-40 nanometer. Okay, but you can see that this gain peak is pretty broad, so you can amplify multiple wavelengths also, right? And you can tune the wavelength, the gain by just tuning the pump wavelength, right? So this shifts along with the pump wavelength. So again, basically you have some length of fiber, and then you send your pump, right? And then you also send your signal which needs to be amplified. And then due to the stimulated Raman scattering, your signal is amplified. Right, so now basically this gives you much more flexibility. You can choose so you can choose the amount of gain by pump out, you can choose where you want your gain by pump wavelength. Okay, so you can also, for example, use multiple pump wavelengths, right? So imagine like I'm using like multiple pump wavelengths here with different powers, right? So now each of them have their own response here, right? So each of them gives me their gain curve, and I scale each by the relative powers in each. So I can have them set up such that when I add all the gain curves up, I get a very flat gain over a very broad wavelength range. Okay, so these multiple wave pump Raman amplifiers, you can really have very broad gain bandwidths here, like up to 100 nanometers or so, roughly, with a very flat gain. Okay, so you can, for example, cover the S, C, L bands, all of them within the same amplifier. Okay, so this, of course, is working on a nonlinear optical effect, not population inversion, right? So there's no population inversion going on. There's just this scattering from the pump to the Stokes, which is mediated through these optical phonons in the medium. So again, you can think of the gain, total gain of the amplifier as something like exponential of a gain coefficient times the length. Right. The nice thing here is that you can use the same optical fiber that you are using for your link. Right. For the EDFA case, you have to use a special fiber you doped with erbium. Here you don't. You can use the same fiber, right? Because this is just a property of the glass itself. So this gain coefficient, again, this we had discussed when we were discussing Raman scattering, depends on the Raman gain coefficient GR and the intensity of the pump. So we can write this as pump power divided by some effective mode area of the mode in the fiber. Okay, again, so recall this GR was about 10 to the minus 14 at near this peak. Okay, so this A effective typically, again, if you take a single mode fiber, is sort of between 50 to 80 micron square. So if you put in the numbers, you can see that I can get a gain of about 20 dB. So G of 100, capital G of 100, with a pump power of about 1 watt and a length of about 1 kilometer. Okay, so you can see that typical lengths required here are much longer. You're talking about kilometers, whereas for the EDFA we are talking about like 10 meters or something. But that's not a problem actually, because as I said, you can use the same fiber that you're using for the link, right? So those are known as distributed Raman amplifiers. So so let's say you have a long link, you just insert your pump for the Raman gain at certain sections, right? And then you can remove the pump. So you get Raman gain for this section. Similarly, you insert your pump. Okay, so basically you can just use parts of your link itself as the Raman amplifier. So these are distributed Raman, called distributed Raman amplifiers, because the amplification is actually happening over a very long section. It's not like, it doesn't look like this what we were talking about, like a length of fiber then amplifier, length of fiber then amplifier. You sort of have the amplifier distributed over a long length. So of course this is if we ignore the fiber losses, but now again if you're talking about distributed Raman amplifiers over kilometers of length, right? Then of course we can't ignore the fiber loss coefficient itself, right? So then instead of e to the GL, again recall for nonlinear optical processes, we had to replace L by this L effective, right? Where L effective was the effective nonlinear length, which goes like this, right? So you can see that when alpha is very small, then this just becomes L. But if alpha is large, or if alpha L is much bigger than 1, L effective just becomes 1 over alpha. Okay, so for again, so 1 over alpha, if alpha is around 0.2 dB per kilometer, you can see L is about 20 kilometers or something, right? So if you typically use distributed Raman amplifiers with lengths like 10, 20 kilometers, then, or longer even, then basically you can see that it doesn't scale with length anymore. Okay. The gain becomes a constant. L is 1 over alpha. So there was a question on EDFA. Typical gain value for EDFA is 30 to 35 dB. So that's sort of the, I would say, the maximum levels that you can get with EDFAs. As we discussed, typically maybe 10 to 30 dB is the range of gains you can get. But yeah, 30, 35 is sort of the upper end of the gain you can get. And the question on, in Raman, forward or backward propagation of pump is used. Either can be used. Sometimes both are also used. You have pumps from both forward and backward directions. But yeah, sometimes forward is used, sometimes backward is used. Because so Raman scattering doesn't depend on the, unlike Brillouin scattering, right, where pump and Stokes have to be counter propagated. Raman scattering doesn't matter if it's forward or backward. But for distributed Raman amplifiers, typically you want, because like if you have pulses traveling, right? Then especially if you use pulses for your pump also, then it's better if they're co-propagating, right? Because if they're counter-propagating, then they will just interact for a very small time and then cross over. For CW, it doesn't matter. If your pump is CW, then I guess forward and backward are sort of the same. But if you use also pulses for your pump, then forward or co-propagating is better. Yeah, and then the noise figures typically for the Raman amplifiers also typically similar to EDFAs, like you can get 4 dB for the good Raman amplifiers.